Hey guys, welcome to our introduction to section 4.6, the fundamental theorem of algebra. Our learning target is I can use the fundamental theorem of algebra to find all solutions of a polynomial equation. So in this video, we're just going to get familiar with the fundamental theorem of algebra and what it really helps us see when we are encountering an equation. So if we look at this table below, it has a bunch of polynomial equations of different degrees, and then it has its solutions and then the total number of solutions. So if we look at this, we can see that in our first equation, 2x minus 1, which is a linear equation, so it's degree 1, we have one solution, which is 1/2. Our quadratic equation, x squared minus 2 equals 0, is degree 2. Its solutions are plus or minus the square root of 2, so that counts as 2 solutions. Our third equation, x cubed minus 8 equals 0, is a cubic, degree 3. It has 3 equations. It has 2, and then it has 1 plus I times the square root of 3 and 1 minus I times the square root of 3. And finally, we have another cubic here, x cubed plus x squared minus x minus 1 equals 0, which is also degree 3, and we have the solutions -1, -1, and 1, which also has 3 solutions. So you might have figured it out already, but if you can tell the relationship between the degree of the polynomial and the number of solutions, notice in our linear, the degree was 1, and we had 1 solution. Quadratic had degree 2, and there were 2 solutions. Both these cubics had 3 solutions. So this relationship is generalized by the fundamental theorem of algebra, which was first proven by the German mathematician Carl Friedrich Gauss. So I have this little screenshot from your book. The theorem is this: if f of x is a polynomial of degree n, where n is greater than 0, so meaning it has to at least have one x in it, like our degree 1 polynomial, then the equation f of x equals 0 has at least one solution in the set of complex numbers. So what that means is, remember, complex numbers are of the form a plus bi, so they actually include both real and imaginary numbers. So this accounts for both real, imaginary, or complex solutions. The corollary to this theorem, which follows the theorem, is that if the degree is n, where n is greater than 0 again, then the equation f of x equals 0 has exactly n solutions. Provided each solution repeated twice is counted as 2 solutions, each solution repeated 3 times is counted as 3 solutions, and so on. Similar to our last equation here that had -1 repeating itself twice, so that counted as 2 solutions for a total of 3. So basically, the fundamental theorem of algebra is this: the degree equals the number of total solutions. So we are just going to do example 1. Tell the number of solutions or zeros given each equation or function. So in letter A, I have the equation x cubed plus 3x squared plus 16x plus 48 equals 0. And I see that the degree is 3. So that's 3 solutions. In letter B, I have the function f of x equals x to the 4th plus 6x cubed plus 12x squared plus 8x. Now, this is just given to us in a different form than A was. A was an equation, so it's asking for solutions. B is a function, so it's asking for zeros, knowing that we'd put 0 right here. It's degree 4, so we would say it has 4 zeros. Moving on to letter C. Letter C is an equation, 4x to the 5th minus 3x cubed plus 2x equals 0. Here's my leading term, which is degree 5. So this equation has 5 solutions. And finally, letter D, f of x equals -x squared plus 5x cubed minus 2. Little curveball here. This is not in standard form. This should be 5x cubed minus x squared minus 2. So my leading term tells me I have degree 3, which means I have 3 zeros of this function. And that is the fundamental theorem of algebra.